So, good morning. We are here again with electromagnetic field. I will now start where we have just finished last time, just a small repetition. We have been talking about the Biot-Savart law, which is a kind of prescription that gives us the electromagnetic field caused not by current traveling from one pole to the other pole of the source, but for just created by a small piece of a current. The small piece is defined by the current and the small element of length IDL. And as the current runs through that element in some direction, this is a vector. Now, recreating the equation, we have the radius vector from the place where the current element exists. So we have some small tiny piece of current, and there is a radius vector to the place of observation. And at this place, the place is seen from the current at some angle or in some radius vector, and this is the formulation we can get. The rest of the formula, I will just make it more visible, depends on the permeability of the media around. Then we have 4 pi in the denominator and the distance squared. So this is quite like the denominator of the equation which tells you the electric field density caused by a charge. That would be a denominator. So then this would look in the same way, but this time we are talking about magnetic field and the numerator is a bit different. We can see it this way. So this is an element of magnetic field that has been created here by an element of the source, which is a small piece of current. Now, we are mostly interested in a magnetic field and its element. So, getting the total out of elements means adding those elements. Provided that the media is linear, we can use superposition and add all those source elements or the effects at the place of observation. Now this is simple as to the equation, but let us start to do it in some case, just to be more aware of what the equation means. So now I am going to put down again the equation on a new sheet of paper, and I will then start with the calculation. By the way, from today's lecture, I will make a new thing. At the end of the lecture, I will put down all the sheets of paper and make a photo of each of them, because it could be much more readable as a photograph than in a video. So you will extract those photos from those sheets. Now, again, the law, a piece of magnetic field, it's a vector, the differential of the magnetic field is given by mu over 4 pi IDL, that's the element vector, vector product with unity radius vector, and divided by the magnitude of the radius vector squared. So let us get now some assignment to solve. Just imagine we have a circle that is created out of a superconductor. well, we will talk superconductors possibly later, but now you already know that they exist. A superconductor is a media with an important property, and that's zero resistivity. And in such a circle, the current, if you get it there somehow, for example by induction, the current would circulate there forever because there are no losses. So we have a circle. The circle seen from one end is something that has a radius small a, and there is a current circulating around. The current I circulates just around, around, and around. Well, was that piece of that current a straight conductor? We already know by Ampere's law that there would be a magnetic field that goes around the conductor. So we know that the presence of the current would be observable using magnetic field sensor. But now we have another question. Let's say we have this circle or ring, metallic superconductive ring, full of current, and we would like to establish the value of the magnetic field on the axis of the ring. So we will redraw it a little bit. We have the ring. Now we have taken the ring and positioned it this way. We have a cut through the middle of the ring. So we have the current that goes this side in and this side out. Here we would have the other part of the ring. So the current goes in this way inside. And now we should establish at the axis the electromagnetic field. To have some coordinates, let's say that we have the coordinate which goes up and down is the coordinate of Z. And at some point we would like to see the magnetic field, to find it out. Well, first we should think a little bit. What causes the field? Well, in fact, this field in this point is a superposition of a number of small sources, that is small elements of current that are positioned all around the ring. Now, for any of those, there is a radius vector. I will draw one of them. So this is a radius vector that connects this element of current, just pointing inside the paper, and this is the radius vector. It points there. So now look at the equation. We have a vector product of IDL vector product with radius. Well, and the result of this is perpendicular to the radius vector. It must be, it's a vector product, and it's perpendicular to the source current element. So the result is in this direction. So this is the piece of magnetic field that is created there due to this small element. This seems quite uncomfortable because, as you can see, if you move around the ring, the direction of that elementary magnetic field would create a kind of cone. So each element produces a magnetic field with a different orientation or different direction, and that would mean or need us to carry out integration in 3 dimensions at least, which is not very comfortable. But if we first think and then do the calculation, we can find out that at the x of the ring, we can always find 2 elements that are directly opposite. One going out, one going in. And those 2 elements would produce a magnetic field over here of the same size, and let's draw it in red, the other one would have caused a magnetic field which has this direction, upstairs. I would possibly use dotted line, the red one does not work very well. So we've got something like this, a blue one dot. So now, if we add those two elementary fields, we would get something like a field going up or down, or which is the direction. Now, this is the result of the vector product, but we have to consider that the field here goes out of the screen, and that is that the magnetic field over here has this orientation. Just opposite. So the vector product of the radius vector is here, and we have the current running out, which gets us this kind of magnetic field. And now we can just tell, okay, if we just add this, the resulting field from both elements, this and this, is behaving very well. If we just take at one time two elements just opposite the ring, so we add this and this, then we add this and this, we add this and this. In that case, we would have the magnetic field running, or the result of those two elements, has only one direction, that is the z coordinate. So in that kind of calculation, we would not have to make an integral in 3 dimensions. We would only integrate a scalar value, and we would know that the resulting field must go down. So this is an important point to find out easily the result. It saves us a lot of computational work if we first think and then make the equation. So by this, we now know that we should find out this value. Now, I would have to add some more into the picture. We have already told that the radius of the ring is small a. Now this is important because we should now find out some prescription for the size of this vector, and this could be done if we observe carefully the triangles. So we have here some triangle, and we are interested in this component, in this side of the triangle. Why? Because this is the elementary part created by the vector source that would give us a small piece to the result. Now this is this side of the triangle. The triangle has one right angle. Now let us find whether there is another triangle which is similar to this one. So we have somehow here another triangle. This is the triangle. It has also one right angle, and it seems to be quite different from this triangle. And we would have to prove that there is one angle which is in this triangle which is the same like this one. So let's start to try that. Does anybody know how to prove that this triangle has one angle not the right one, but one of those, which is of the same size as this angle. I will leave 1 minute for you to think it about, to think it over. Okay, no suggestions? So I will try to do it on my own. Please observe this situation. We have some angle here. Let us denote it by alpha. This is the angle that has one arm on the ring, and the other arm is the radius vector pointing to the point of observation. Now, this radius vector is perpendicular to the magnetic field created by the element. So we have a right angle over here. This is just by the law of Biot-Savart. Well, okay, now we have here a triangle that has here one angle which is the right angle. Now it must hold that, and we have the other triangle which has a right angle and the angle alpha. Now if this angle is right, it means that it is cut by this side of the triangle into two parts, and these two parts must be in the same division, like this angle and this angle. You have already this angle over here, so it must follow that this angle is alpha. And now we have proven that we have two triangles with the same angles, because the sum of all the angles of a triangle must be pi radians. So we now know that we have here created the situation where we know that those two triangles must have the same ratio of proper sides. So now we can establish an equation which would say, okay, we have the total magnetic field here, and we can get this part of it using the similarity between triangles. So let's call this B with apostrophe, and let's call this B. Oh, this is D, B, the elementary B. So B with apostrophe over dB. This is the side which is solved. Now this is the largest side of the triangle. And now we have the same or similar triangle here, which tells us that we must have this over this as the same ratio. So this over this is small a divided by the radius vector. To be correct by the magnitude of the radius vector. So now we can get this into an equation. We should note that the radius vector, the size of the radius vector, can be obtained by using the Pythagoras equation. So we would say, okay, a squared plus z squared, summing those two and making square root, we get just the r. So, okay, we can tell now that b over db is equivalent to a over a square root of a squared plus z squared. Well, that's nice. And we should possibly proceed. Now we should establish db. db could be established just using this equation. We would need now to find out the angle of the radius vector and the current. Now just watch it. We have the element which is a radius vector oriented in this way, and as you can find out, at any point the radius vector to the point of observation with the circle, just those are the elements on the circle, and you have a point of observation on the axis. So from any of those points you observe the result at a right angle. So in that manner we can substitute this result as to its magnitude by an ordinary product. We can get rid of vector product at this moment because we already know the direction and orientation of the result. The field would be going down in this case. So we know that it's oriented against the z-axis. Now we can proceed. Bearing that in mind, we can put down b with apostrophe as an equation where b apostrophe is first a over square root of a squared plus z squared. That's the first equation, and then it continues multiplied by, and it must be multiplied by I dl over r squared, and r squared is a squared plus z squared. So we now have the equation for a piece of b in this direction at the x of the ring. What we still have to do is to add all those small pieces together, or to set up an integral. So I will...
Excuse me?
Yes?
I did not understand like lower part of that second part where a squared plus z squared. Shouldn't it be square in square roots?
Well, not.
I do not.
But let's repeat it once more. This part of the equation here gets, well, the numerator, which you do not question, and then there is the denominator, and that is the r squared.
I didn't notice this.
So if we have r as a square root, if we square it, we get the inside of the square root. So this is just what we have not put here is 1 over mu over 4 pi. That's important. Now I will rewrite this equation. Unfortunately, the paper is not big enough. So let us rewrite this equation once more. So we would have the small piece of b with apostrophe, which is a differential, and that is a over. I will sum those two brackets, so that's a squared plus z squared raised to 3 halves. That is the square root multiplied by the bracket itself. Then we have got here mu I dl, and we have 4 pi in the denominator. So we have rewritten this equation, and in order to get the result we would have to carry out integration just around the ring. Now this is an important point, how to make it. If we have a piece of the ring, we cut an element out of that. We have somewhere the center of the ring, so that this is the radius A. We have here some length of the element, the dl. This is the dl, but if we want to carry out the integration around the ring, we would have to find out the attitude of dl to the angle we have already used alpha, so to the angle beta, against which we would make the integration just around the ring. And now this could be done. If we know the radius, then this length for small radii, dl, must be beta multiplied by a, or d beta, an element of the angle, multiplied by the length, and the angle runs from 0 to 2 pi's. Now we know that we can rewrite this into an integral form, which would look somehow like b, I will mark it b total, is equivalent to an integral from 0 to 2 pi. The integrand would be a mu I over a squared plus z squared raised to 3 halves multiplied by 4 pi d beta. Well, okay, so we have the integral. Fortunately, it's quite simple. In fact, anything in the integrand here is constant against beta. So, in fact, what we do is we just put it in front of the integral, and then we know that the integral of, oh, sorry, I made a mistake. I should put her there, the a, because the dl is a d beta. So this is the result. But the a is already here. So, okay, now I can make the final calculation, which is the total B, which we know is oriented downside along the z-axis but against its orientation, would be a mu I over a squared plus z squared raised to 3 halves multiplied by 4 pi, and now the result of this integration is beta. We integrated a constant, so we get beta, and we put the upper bound and lower bound, and from that we would receive 2 pi. Now we cancel this, and we have got the result. And the result is not correct. Now you have been watching the whole thing, so please, what the mistake is? So we have to return back. I promised a competition for today, so I will wait with this and leave you to find it out. But please don't do it now, because we will go on with the lecture in 5 minutes. Who sends me first the correct solution, and you can use the textbook, will win a prize. So now we will wait 5 minutes, because we have been already working for some time, and after that coffee time I will continue with a question which is new today, and that's inductance. See you in 5 minutes. Well, after all, you can do the result within that 5 minutes and send it directly to my email. It's not very much time consuming, but that's a competition.